Hello all. Today we're going to be starting chapter 13. In chapter 13 we're talking all about higher degree polynomials. And we're going to start just by talking about some graphs of polynomials and just doing a little bit of vocab. There's really no calculation, so to speak, for this chapter. In editing, we're going to talk about two pieces of vocabulary here today. The first two pieces are going to be called the extrema and the second piece is going to be zeros. So a zero is just where the graph crosses the x-axis. So it looks to me like I have 3 zeros specifically. The extrema are the relative high and low points of the graph. So here we have 2 extrema. Now this extrema we call the local maximum, because while it's the highest point in its area, it's not the highest point on the graph overall. We notice that this graph is going off to infinity, so there are points higher than that maximum, but relative to that area, it's the highest, so we'll call it a local. This one over here is also a local, but it's a minimum, because again, relative to its area, it's the lowest point, but it's certainly not the lowest point overall, because we have this end going down. Now, because these both ends of our graph are going either to positive infinity or negative infinity, there is no global maximum or minimum. There's no absolute highest point, because since the graph is going on forever, it is not something we have to, or that we can find. There is no specific point. So if we graph this function now on our calculator, using the same window that's listed here, we can find the specific values for these zeros and max and min, our local maximum, local minimum, by using our calculator. So if I press the second and trace command, if I select from this set of options, notice there's a 0 command. So let's find one of these zeros first. So if I select that, the calculator is then going to ask me some questions down here at the bottom. So let's say we're finding this 0 first. We have to do them one at a time. So the first thing it asks me is for a left bound. So I'm going to move my cursor somewhere on the left side of that 0, so somewhere over here. So if I just use my left arrow, it's going to move my cursor for say to here. So that's somewhere left of it. Now press enter. Now it asks me for a right bound. So I'll move my cursor somewhere to the right of it, over here. So that looks good. So I'll press enter. And then it asks me for a guess, so I'll move close to it and press enter. So one of my zeros is -1, 0. So to find the maximum, and if you wanted to find these other 2 zeros, you could repeat that same process. To find a maximum, I'm going to press, again, second and trace, and this time select the maximum command. So again, it's going to ask me these same 3 questions, so somewhere left of that maximum, so I'll press enter. I'll move somewhere to the right of it, so that looks good, doesn't really matter where it's at. Then press enter, and then I guess I'll move somewhere close and press enter. And it gives me the coordinates then for that maximum. And if I wanted to find the minimum, again I'll press second and trace, select the minimum command this time, and it's going to ask me those same 3 questions. So left bound, so I'll move somewhere left of it, press enter, somewhere to the right of it, press enter, and then I guess and press enter. And again, it's given me the coordinates for that one. The next thing that's up, through the magic of editing, we have this nice little theorem here. This theorem says a polynomial of degree n will have at most n zeros and at most n-1 extrema. So if we take this and we look at an example, let's say we have the function f of x equals 3x to the fourth minus 5x to the third plus 2x plus 2. We really just care about the degree. So remember, the degree is the largest exponent on the variable. So in our case, the degree is n. So that tells me I can have at most 4 zeros and 3 extreme 1. Okay, so we have n zeros, since n is 4, and n minus 1 extrema, since n is 4. And that's it. So the next thing we want to talk about is end behavior. Behavior for a function is describing what the arrows at the end of the function are doing at the end, on the graph, the arrows on the graph. Or really, it's just describing what's happening as the values of x get very large or very small. So we have a special notation that we're going to use to describe this. This is probably new for everybody involved. This is called a limits notation. So the notation for a limit might look something like this. So the way we read that symbol is we say the limit as x approaches infinity of f of x, and then we'd say is whatever that end behavior is. So this limit that we're describing here is for when x's are getting very, very big, because we're approaching positive infinity. So one way we can do that is we can build out a table of y values and look at what happens as x gets progressively larger. So we can make an f of x table. So let's say we want to find the limits here for the end behavior, or find the end behavior and describe them using limits. So let's pick some progressively larger values for x. So maybe 100, say 1,000, and then let's say 10,000. And what I'll do is I'll just go into my calculator and plug these values in for x. Oops. Forgot the parenthesis at the end of that. I don't think it'll make a difference, but let's just make sure we get it. Okay, so we have 1,959,901. And now let's replace that 100 with 1,000. So I'll press second and enter to recall the last thing I had, and then do second and delete, which will allow me to insert another 0 in for each of these. Okay. So when I do that, I get 1,995,999,001. And if I do this for 10,000, basically here we're not so much concerned with the actual y values. We're just kind of concerned with the pattern that's going on. So again, I'm going to go ahead and insert another 0 into each of these. And that gives me basically 2 times 10 to the 12th. That's 2 with 12 zeros after it. So what we're seeing is, as x is getting bigger, y is also getting bigger. So we'd write the limit as x approaches positive infinity of f of x is equal to, well, positive infinity. Now there's two ends to the graph, though. There's, what's happening at the right end and what's happening at the left end. So let's do the same thing, but this time let's look at the left end. Let's look at what's happening as those values for x are getting progressively smaller and smaller. So if I press second and enter, and I'm just going to start with negative 10,000 because it's going to make it a little bit easier typing these things in, to just insert that negative sign first without having to delete anything. So I get about negative 2 times 10 to the 12th. Again, I'm not so much concerned with the actual values. I'm just kind of looking at the pattern. So here we saw things were getting progressively bigger and bigger and bigger. Let's see what happens. Oops. See what happens now when I do a negative 1,000. So when I do that, I get negative 3,998,999. And when I do negative 100, we get negative 2,038,899. So if I look at what's happening to these y-coordinates as we move more and more negative on the x-axis, is that those y values are getting smaller and smaller and smaller. So write the limit as x approaches negative infinity of f of x is equal to negative infinity. Now, that's one way of approaching this, but some of us probably remember from our previous course that if we look at the leading coefficient and the degree, we can figure out what these end behaviors are without actually having to create a table of values. So if the leading coefficient is positive and the degree is even, then both limits are the same. They're both going to be positive infinity. So if the leading coefficient is positive, but the degree is odd, here the limits are going to be different. And this is exactly the case that we had up here, right? Notice leading coefficient is positive, but the degree is odd. So we have that same result. If the leading coefficient is negative and the degree is even, again, the limits are going to be the same. But here, they're going to both be negative infinity. And the last situation, where the leading coefficient is negative and the degree is odd, here it's going to be kind of the opposite of what we saw in our example just a moment ago. Okay. So you could do this as well, instead of trying to compute these guys by hand using a table. You could also just use these rules here. And you might have remembered these guys from your Algebra 3-4 course. We're just writing these limits a little bit differently or these end behaviors a little differently with this limit notation. But it's the same ideas of what you've seen before. Okay. In section 13.2, we're going to be looking at finding the zeros of polynomial functions. So remember, we said the 0 was the place where the graph crosses the y-axis. I'm sorry, the x-axis, which means its y-coordinate is 0, aka f of x is equal to 0. So we're looking for where the f of x is equal to 0. So to solve an equation that looks like this, we're going to try to do this by factoring. So the first thing you look for when we're trying to factor something is a greatest common factor. Notice if I look at each term, I see a greatest common factor of x. So I'm going to factor that off. Okay, and then what I'm left with is a quadratic part. So I know that I can solve any quadratic part either by factoring, or if I have to, I can use the quadratic formula, or even if you just prefer. So I'll apply the zero product property here. So I can say that x is equal to 0, and then x squared minus 6x minus 8 is equal to 0. So x equals 0, that's solved already. For x squared minus 6x minus 8 equal to 0, since the leading coefficient is 1, I would start by trying to factor this. So I'd be looking for two numbers that multiply to give me negative 8 and add to give me negative 6. Think about that for a moment. You should come to the conclusion there are no two such integers that'll do that. That's okay though, because we have a formula to deal with this. So negative b plus or minus the square root b squared minus 4ac all over 2 times a. That's the quadratic formula. So negative of a negative is positive. So we have 36 minus a negative 32. So that would be 68 over 2. And then the last thing I'd want to do is to check to see if 64 can, or the square root of 64 can be reduced. Or sorry, square root of 68 can be reduced. So it definitely can. So we can have the square root of 2 and the square root of 34. And square root of 34, square root of 2, and the square root of 17. Square root of 2 times square root of 2 is positive 2. Or the square root of 4, which is just is the same thing as 2. And then hopefully you notice that because each of the coefficients in the numerator are divisible by 2 and the denominator is divisible by 2, we can reduce this to just 3 plus or minus square root 17. So those are my 3 zeros. Notice I knew there was going to be 3 zeros because the degree was 3 for the polynomial. 1 0 is here at x equals 0. And then I have 2 zeros here. Right? I have 3 plus the square root of 17. And then I also have 3 minus the square root of 17. Okay. So the next example, it says find the zeros and the multiplicity of the zeros for the function. When we say multiplicity, we're just talking about the number of times that solution occurs. So in the previous example, each of these solutions, 0, 3 plus square root of 17 and 3 minus the square root of 17 all have multiplicity 1. They just occur one time when we did the solving process. Let's look at this next example, and something different is going to happen here. So again, f of x, I'm going to replace with a 0 because we're looking for the zeros for the function. And I'm going to start by taking a greatest common factor. So if I take out an x, and I'm left with two pieces, a linear part and a quadratic part. Both of those I can solve. So I'll apply the zero product property and set each piece equal to 0. X equals 0 is already solved for me, so there's nothing more to do there. And now I'm left with x squared plus 6x plus 9. So I'm going to try to factor this. Since the leading coefficient is 1, it should be easy if it's possible. Two things that multiply to give me 9 and add to give me 6 are 3 and 3. So I know that factors down to x plus 3 times x plus 3. So when I apply the zero product property again and solve, I get x equals -3 and x equals -3 a separate time. So because I've got the same solution happening more than once, I can say this, that there are two solutions, 0 and -3, but -3 has multiplicity 2 because that solution occurred 2 times when we solved. Okay with that? Good. So our last example here says a company wants to create a cardboard box with an open top. So think about like, like the box that the copy paper comes on that has a lid. Imagine the bottom part without the lid. That's what we mean by open top. The box needs to have a volume of 500 cubic inches and is to be created by cutting squares from each corner of a rectangular piece of cardboard in order to create tabs to fold up. So I've drawn that figure here. So these shaded pieces are the parts that are going to be cut out. And then we'd fold here along the dashed lines, and you'd end up with a box. The piece of cardboard is 26 inches by 20 inches. So 26 inches by 20 inches. And we want what size squares should be cut from the corners in order to create the proper volume. So we don't know what that is, so I'm going to say that the length of each of these squares is going to be x. So since they're squares, they have the same length and width, so they're just x by x pieces. So I know volume is equal to length times width times height. So what I need to do is figure out the length and width and height of this box that I'm going to make. So the length can be that side, the width can be that side, and then we fold it up, the height would be like one of these edges. Okay? So the height should be easy since this is a square. I know that that's just x. Now if I look at the width here, the green piece, we can figure out what that is in terms of x. So we know that this whole side is 26. But we've cut off x from each end of it. So the green piece then would be 26 minus 2x. Similarly, if I look at the yellow piece here, this whole side is 20, but I've cut off x from each end of it. So that would be 20 minus 2x. And I know this volume needs to be 500. So this is the equation that I'm going to solve. To do this, I'm going to start by FOILing this out. So, to save you some time, I have this worked out. I get 520x minus 92x plus 4x cubed. And if I'm looking for, to solve this, what I'm going to do is I'm going to get it equal to 0. So I'm going to subtract that 500 over. And I'm going to write this kind of in standard form. Oops, that's 92x squared, excuse me. I'll write it like this. And then what I'm going to do is graph this and look for the zeros. I'm choosing to graph this because looking at this, there's no obvious factoring for me to do here to be able to solve this. And if I can't solve it by factoring, graphing is a nice alternative. So to solve this by graphing, I'm going to go ahead and type in my function here. Do 4 x cubed minus 92x squared plus 520x minus 500. And the window here, if I think about it for a moment, should be pretty obvious to us. So the biggest value x could have would be 10, because if x was more than 10, you wouldn't have any side here. So and x is also a length, so I know it has to be at least 0. And it can't be any bigger than 10, because then if it was like 11, you'd cut 11 from here, and you'd have only 9 left over here, and you couldn't do anything. So I know that it's somewhere between 0 and 10. And the y's, I don't really know what that's going to look like. So I'm just going to pick something kind of big, maybe 100. And if I have to, I can make that number bigger or smaller depending on the picture I get. The important part was kind of getting a good idea on the bound here for my x's. So let's hit graph. So there's my function. And I don't really care. I did a dumb thing here. Let's go back. I want to be able to see where it crosses the x-axis, so I don't know why I would have picked, something that wasn't, I needed to be able to see where it crosses, so I need to see this point. So before, when I had just the x-axis here, that was a dumb thing, because I need to see where it's crossing. And I don't really care about the top. All I care about is the places where it's crossing. So if I do second and trace, and then do the 0 command, and I'm going to move my, let's find this one first. So I'm just going to move my cursor. So notice when you can see where the cursor is at. So it's at 3.5, so it's up here somewhere off the screen. But that's okay, it doesn't really matter. I'm just going to oh my goodness. Alright, I'm just going to keep pressing left till I can see it. And I'm going to do left bound, so now it's left of where that 0 is, so I'll press enter. And right bound, so I'll do that a couple of times, it's right. And then I guess, so that looks fine. And so one of my solutions is 1.20. So let's write that down. Halfway done, we have another possible solution over here. So I'll press second and trace again. Again, select the 0 command. We're going to move somewhere over here to find a left bound, so I'll just press the right arrow about 1,000,000 times until I see my cursor start to show up again. There we go, so that looks good. Press enter. And a right bound, so I need something over here. So I'll move my cursor a couple of times. That looks good. Press enter. And then move over to a guess. So I just go back one spot and press enter. And I have 702 as my other solution. Now, you might be asking yourself, gee, how do I know which one I should use? Well, it doesn't matter, in fact. So you can pick either one. They're all going to be okay. So if we wanted the actual dimensions of this box, so the length here, we said is going to be 26 minus 2x. So when x is 1.2, I get this to be 23.6. The width we said was 20 minus 2x. So when we do that, we get 17.6, and the height is that 1.2. If we pick the other dimension, the length is 26 minus 2x, so that comes out to be 10.8. Oops, I took that in wrong. 11.96. The width is 20 minus 2x. So that's 5.96. And the height is 7.02. And if you really wanted to check, you could just multiply these three dimensions together, and you should get about 500. So when I do this one, I get 498.432. Why didn't we get exactly 500? Because as you saw, we rounded these. So that's why we're not getting it to be exact, but that's okay for what we're doing here. If I take the other three dimensions, volume here we get is 500,039. And again, I guess these are all inches. So again, all this down here was just me checking and like extending this answer out. The question really just needed these two numbers here. Okay, and that's it for this section. Have a good day.